Okay, so I'm going to show a couple of videos. I don't know if I'm going to give you homework actually today. I just want to kind of chat about things. I'm going to put a tack on the voltaic cell thing. We might do an illustration. So I might illustrate something and expect you to write it down, and then you just upload it as your notes for today. And when you do that, you'll get credit for what we've done. So first of all, I'm going to show you a couple pictures, movies. Everybody looks, I kept promising movies, and here's your first movie. And what I got to do is set this up that you guys can see your computer sound. It optimized for a video clip.
Is this what we're taking notes on?
Yeah, but I got to draw it all back out. So let's just watch a video real quick, okay?
Okay.
Here we go.
Observe the construction of a voltaic cell. The simple cell or voltaic cell consists of two electrodes, one of copper and the other of zinc, dipped in a solution of dilute sulfuric acid in a glass vessel. On connecting the two electrodes externally with a piece of wire, current flows from copper to zinc outside the cell and from zinc to copper inside it. The copper electrode is the positive pole or copper rod of the cell, and zinc is the negative pole or zinc rod of cell. The electrolyte is dilute sulfuric acid. How is the action of the cell? The action of the cell is explained in terms of the motion of the charged ions. At the zinc rod, the zinc atoms get ionized and pass into solution as Zn++ ions. This leaves the zinc rod with 2 electrons more, making it negative. What happens at the copper rods? At the same time, 2 hydrogen ions, 2H++, are discharged at the copper rod by taking the 2 electrons. This makes the copper rod positive. As long as excess electrons are available on the zinc electrode, this process goes on and a current flows continuously in external circuit. This simple cell is thus seen as a device which converts chemical energy into electrical energy.
Is electrical a word?
Yes,
Really?
I think so.
What is electric?
No, electrical. What do you call an electrical circuit? Like,
Electric?
What about like electrical engineering? Like, isn't that a thing?
electric
She got you
engineer.
there, Morgan. She got you there.
I'm an electric engineer.
I've never
No, I see what you're saying now. Like, I don't, like, I understand.
Why is Cam just like a shadow?
That's him always. Even when we had school.
You should have seen Aiden's computer yesterday. He broke and screws went flying across his room.
Why do we all go to the same spot?
I was yelling at you for the last 5 minutes, and I was on mute. So you
But wait, Aiden, you fixed your camera?
solid.
No, I took my sister's.
Okay,
Where's Aiden? Oh,
watch this. So we have copper, right, plus zinc, okay? And zinc is going to give its electrons up, okay, in the sense that it becomes what? It becomes, if it gives up its electrons, it is going to be reduced or oxidized. It's going to be oxidized. So I have to make this thing a little more interesting for what we're doing. This is called a voltaic cell and not a galvanic cell, okay? So in some ways, we have this guy sitting out here in solution, remember? And when you did all your half reactions, one of your thing was either H plus or we had OH in the mix that were involved as part of the medium for all this thing to occur, okay? So this right here is very interesting. You could have 2 things. And if we were in the lab, I would totally do this. You put some acid in there, you have a piece of copper, I had strip wire, I took a piece of zinc, stick it in there. You can hook it up to a voltmeter. And eventually what happens is the zinc, this part would actually dissolve. It disintegrates. And it's really, really strange. And the reason why is that every time a zinc atom comes off, it goes into solution, okay? And it basically is displacing the 2 hydrogen ions, which are going to basically go up this way, up off the rod. That's the positive effect. This actual cell will burn out eventually, because eventually this gets all neutralized, okay?
Wait, so which way would like the current be going? From the copper like through the light bulb, or from the zinc through the light bulb?
Well, the zinc, because it's going to be negative.
Okay.
The negative ion goes here and comes out this way, right?
Can you draw that?
No, don't draw this. This is not the one I want you to see. First, I got to clear this because that's crazy. Okay? So we're going to look at, this is actually more of what's really kind of being what's done. Now, let me optimize this so you guys can see this all the way through. And this is the one we're going to totally dissect. Okay. So for all practical reasons, this is the one we're going to focus on because this is more of how we've done our experiments. Let's go down here and hit play. Boom.
Is it playing?
It's not playing for me.
It's not playing for me.
It's not playing for me.
I was hoping it wasn't just me.
I know that was just me.
Oh, you're invisible.
Let's zoom into the atomic scale and see how this cell operates. Here, at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Each atom loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which deposits on the bar. Therefore, as the cell runs, the zinc anode becomes lighter and the copper cathode heavier. Now let's close in to see the role of the salt bridge. The non-reactive sodium and nitrate ions of the salt bridge prevent the buildup of charge that would occur as zinc ions enter the anode solution and copper 2 ions leave the cathode solution. Such a charge buildup would halt cell operation. In the anode compartment, nitrate ions leave the salt bridge to balance the gain of positive charge as zinc ions enter the solution. Some zinc ions also enter the salt bridge. In the cathode compartment, sodium ions leave the salt bridge and nitrate ions enter it to balance the loss of positive charge as copper 2 ions leave the solution and are reduced at the cathode.
Interesting.
Wow. Ready? So what we're going to do as friends, we're going to draw this whole thing out to explain what is occurring. Okay. So I'm sure you guys are all excited about drawing because nothing's more fun than drawing, right?
No.
Yeah.
All right. So basically, who mocked my yeah? I don't understand.
Luke.
No, I said no.
Okay. All right. Well, at least you're honest about it. Okay. Here we go. So you guys should be seeing my paint. Do you guys see paint?
Yeah.
Okay. So what we're going to do is I'm going to actually draw, and you guys are going to draw with me what we just did, what we just saw. So I'm gonna make a box, right?
Squares.
Okay. I'm gonna make a square box, and I'm gonna make another box, and this is actually supposed to be my jars. Okay. There's 1, and there's 2. Okay. Now I'm also going to make what appears to be a salt bridge. I'm going to try to do my best for doing this. It's probably going to suck, but I don't really care. But for all practical reasons, I make a tube that goes like this, right? And I'm going to make another tube that goes from here down into this guy. Nice. That looks really good. And I make another tube that goes from here down into here. Okay. Now, see if I can do this. I'm going to zoom in a little bit. Boom. Oh, that looks good. Okay. Zoom in. Boom. Wait, I want to zoom in. See if I can get this done. And I'm being very artistic just for you. Okay. So I'm going to grab my eraser and I'm going to take care of this. Look at the artwork. You guys, are you not
Oh
smiling?
yes.
I am just impressing myself in the very least, doing the most minimal things to make my life better. And here we go. Ready? Okay. Now I'm going to zoom out, right? So that's kind of my setup, okay? The one thing I also am going to make, I'm going to actually make a copper wire, right? So I'm going to make a wire that goes up here. Okay, I'm going to go up. I'm going to make another wire that goes from here. Whoa, I don't want to go there. Edit, undo what I just did. Can I just draw it? Can I just draw this thing? Why is it acting so?
No, put that end at the other corner where you're trying to go, and then pull it up. Pull it all the way across, like straight. No, no, no. Like,
Josh.
no, at the beginning.
You
Make it
make the
flat and
whole
then pull it
thing.
up.
You put the
Like-
2 endpoints on each side. You
no,
put your,
No,
No,
go back to
silly.
the curve.
the
Go to the
horizontal
curve
one.
one. Go to the curve one.
do the curved one.
Do the curve. Click on. Delete.
No.
Ah!
Holy.
Erase them.
Go back to the curve one.
Yeah.
No. No.
That's harder than the chemistry.
No. No.
I can't do the curve. It's not working.
Pull a straight
no,
line. No, no,
no,
no.
No.
Just
Straight
go like
line.
this, like.
Put
To
that
the other
endpoint on
corner.
the
Yeah,
other
yeah.
side.
Yes.
Stop. Oh no.
It's not bending.
Go to the other corner. No, it's gonna bend later. You have to make it go. Go back. Go back. Go back.
I decline your remote access. I'll figure this out. What am I supposed to do? I put it here?
Okay. So click on the corner you want to start.
Put,
Okay.
And go straight horizontally to the other corner where you want to end.
Okay.
Yes. Now hit done and then pull it up. There you go. That's better.
That's the best you can give. That's
Yeah.
horrible.
That's good.
is that what it's meant to look like?
Wait, dude, can't you pull it again, like on the?
Like keep like forming it.
Yeah, on
Yeah.
the sides.
I don't know. I don't think it does that. It's
Go to your little pointer thingy.
What?
Like, can't you just get like a normal mouse and then pull it?
I am using a normal mouse right now. It's just not doing what it's supposed to do. I just, you know what I gotta do? I got a better idea. I'm always filled with better ideas. I like what you just showed me. So I'm gonna take, edit, undo that, right? I'll get my curve line.
He's gonna go halfway.
I'm gonna go
Oh
from
no, he's
here.
not.
And you said I'm gonna pull this thing up. Well, that evens. Let's go again. All this for a drawing. This is like, wow. This is
Dedication.
Okay, we're gonna do this. I have an idea. Watch this. I'm gonna grab this. I'm gonna bend this like this. That's good. Watch, right? And then I'm gonna use. Can I move the whole thing up? I want to move that up. How do I move it up? Oh God.
Oh boy.
Oh no, it's not.
Or you could go halfway in between them and just do 2 of them.
2 curves.
Yeah, 2 curves.
I got it. I got here,
And then he makes it curved.
and then I grab this one,
Boy.
Oh yeah.
and then I grab a curve line
Yeah.
here,
There we are.
and then I grab the center and burn it. There we go. Why'd you guys make it so hard?
Why not?
I know. Okay, boom. That's gonna be good enough, right? So I'm gonna put this in here. I'm gonna put another thing here. Right. I'm gonna put this here. Everybody good? And I'm gonna change the color of this thing. I fill it. Did I fill this color? Wait. Okay. And I'm gonna grab another bar. And I change the color for this one. Make this color. And let's grab this guy. And he's this thing. Okay. So then I'm gonna view. I'm gonna zoom out a little bit.
Did we
God, just-
color them?
I don't have colors.
Well, try your best. What you're doing is just trying to more or less, not mimic what I've done, but you come up with your own variety of this. And we're going to explain what's happening. This should be somewhat fascinating, okay? We are going to make the sodium bridge, okay? I'm going to use 2 different compounds for this. I'm going to use sodium, I'm going to say sodium chloride. It makes it a little easier for doing things.
Knackle.
So I'm going to put NaCl in the center of this thing. See if I can get this in here. NaC.
Holy.
Yeah, I got to bring that down just a little. So let's go down.
Okay.
Let's go down to 10, 11. No, you're not going to let me do this, are you?
5.
Paint is one of the rudest little guys for doing things. Let's go down to 9. Okay, let's go to 8. Okay, that's good enough, right? And oh god, I wanted that smaller, and it's Can I move this thing?
If it doesn't fit, make it.
Take that one.
Unfortunately, it's such a commitment in Paint. It is not the best program for doing stuff in, but it just never has been. It's just something that I could do it so I can save it and jump around. But let's just put NaCl here. Even now, it still sucks. Jeez, Lord. Oh, I could, you know what I could do? I could just grab an already made picture and put it up, but I'm dedicated to the cause. That's what I'm going to draw this with you because I feel like you guys got to draw it. I got to draw it, right? So I'm going to put another one here. I'm going to put this guy. He is going to be of the rods I'm going to make. I'm going to make him zinc, right? So I'm going to put 2 letters on here, ZN, okay? My advice is you join in on that fun. Oh, crap. I can't move you. I should have made you much bigger for doing this. You're on 8. Okay, maybe I can make you, wait, highlight you. I'm gonna make you 6. Maybe you can see it better. Okay, hit enter, boom. Ah, much better. You're actually gonna fit inside the stick. Let's see. Come on, you gotta go over. Oh, you jerk. Oh my God. All right.
Dr. Duick,
So, yeah.
should we go outside? Because it's like super windy. Like, couldn't that just be like Corona air?
What?
Should we even go outside if it's windy? Which it is. Like, is that gonna be like Corona air?
Is it?
Just like
You
blowing
just said
around
it was
the
airborne.
clouds.
I don't know. I don't know about that. I don't think so.
Oh.
Good thought, Ryder.
Good idea. Good idea. It's the effort that counts.
What the?
Wait.
I think that's cheating.
I have confusion.
Is it cheating?
Yeah, it definitely is.
Are we supposed? Our drawings supposed to look like that?
No, sweetie, no.
Sweetie. Oh, you guys are such funny people. This is what makes life so much better. I don't know why this is down here. Oh, I moved you guys down here. Let's go back here. All right. I gotta move this up. It's a way. Let's go here. File. Let's do this. There. I cheated. I'm cheating, and we're going to illustrate this as we go because obviously I'm really bad at drawing, and I don't want to.
Cheating isn't good.
Well, I know it's not good, but in this case, we got to do it because it's sort of confusing, right? So to illustrate what's going on, and I'm going to have to smaller active window to put this here so I can see what's going on. We do know there's a couple of things occurring on both of these things, all right? So first of all,
Are we making
We
our
have-
drawings look like this?
yeah.
So it's
Why
not.
not?
Easy, right? So we have a cocktail of zinc sulfate, and we have a cocktail of copper sulfate. So the only good thing about this is I can write out an equation here to the outside showing you what's going on, okay? So this is what is occurring, right? Let me grab my pen, right? And I'll go home, and we'll grab ourselves something to write with, okay? So we have zinc sulfate, ZnSO4, plus, right, Cu, right, SO4, right, yields All right, these are obviously spectator ions induced, right? What happens in this thing?
Is the zinc a 2 minus?
No, it's a metal. It's plus
Wait.
2, right?
So Dr. Dick, does the
Yeah.
copper become an ion?
Huh?
Does the copper like come off and become an ion?
Yeah. One second, I gotta change this. I just messed up. Wait. This is really the chemical reaction. So if we look at this, zinc plus copper sulfate yields copper and plus, right? This is kind of crazy. Plus zinc sulfate. Okay, now watch what happens. If we think about what's going on, this actually doesn't really matter. It is a spectator ion on both of these things. Okay, we do know one thing that happens. Okay, and I'm just blowing this up so we could get this big lesson out of the way. In the picture, copper, and I'm going to pull this down to see this thing, right? It's on select. Fair enough. Let's go here. Copper's going to come in, right? So copper as an ion, I'm going to put plus 2 here. And here's zinc, all right, as a solid. He's the bar. Zinc is going to basically donate its 2 electrons to copper. And in doing so, copper becomes a solid and it's going to be deposited on the bar. So if I was to draw these 2 bars, okay, here's the zinc bar right here, okay? And I'm going to make him like whatever color this is, I don't know, right? And then I'm going to grab this and here's my copper bar, okay? I'm going to make it this color, right? This is in the beginning. As the chemical process takes place, I'm going to do this. And oh, that's not what I want to do. Edit undo. As the chemical process takes place, okay, we're going to have this occur. This, I don't know what color that was, but I'll find it out in a second. My zinc bar, okay, and I'm going to try to put it like this. On the one hand, I actually put them in the wrong spot. Can I change that real quick? That's bothering me. I'd rather put it correctly. Hold on a second. I want the bars to be in the same spot on both sides, so just bear with me. So I went zinc here, ZN. That's not the color I want. Everything's always a mess in the morning. Look at this here. Oh, all right, let's go black. There we go. So we have zinc. Zinc, right? And it's going to be plus 2. And we'll have copper being O, okay? Following what we have going on here. So the zinc color, what color is that? Is that the blue one? I guess. It's this one. I didn't want that. Let's go this color, right? And I'm going to actually chew this up a little bit, okay? So in doing so, I guess it would be more of, when I say chewed up, it's going to be, I'm going to grab an eraser. I'm going to do this. I'm going to do, the zinc bar will degrade, okay? And why that's occurring, if we think about it, is that the zinc as a piece of metal, it's going to go from O, right? Go off into solution as Zn plus 2. And what happens is it's going to basically end up in solution. On the other hand, let me grab the bar for copper, which is this. Oh God, that's bad.
Does copper get bigger?
And copper is going to get bigger. Very well played. And the reason why is it's going to go through a thing called deposition. And as the electrons are being transferred, right, I'm going to make myself a couple of these guys, really small ones out here. 1, 2, 3. This is copper ions, right? And I'm going to write this the outside copper. So, no, okay. And then I'm going to put this guy. I have this guy called copper plus 2, Cu plus 2. It's going to come in, and when it attaches, it becomes CuO. And when that happens, you're going to end up with a bunch of these guys like this, all attaching to them, right? One, let's do another one. Okay, I don't want to do that. Let's do this. Basically, I just use a paintbrush for this, right? it's going to go through deposition, and you'll see one side of this thing start to get filled with stuff, okay? So the zinc is being degraded, essentially. It's just the bar itself is going to go from a solid to an ion. It starts to float in solution. It goes away. Copper as an ion in solution is going to come over and deposit on this bar, and eventually it gets bigger. That's kind of what's happening. So when you see an oxidation reaction occurring, okay, that's the strange thing, is that you are kind of in a weird system of the electron transfer, which is going across the top of this thing. And we see if we're going from 0 to +2. What does that mean? That means if we look at that, these are 2 electrons. Back when I was drawing the first parts of these pictures, you're like, I 2 on this side and we have something going on underneath. But the idea is that electron transfer allows these ions here, these are electrons that are coming down this rod here, 2e. And when it comes down, it's able to click onto the ions in solution, and in doing so, it makes it deposit. So that's what this picture down here is supposed to be illustrating. This is copper ions in solution. Copper sulfate is my solution. The copper ions themselves, as you can see at this point, are just coming in. These are all +2, right? So if I was to draw, let me get a really small line for this. So if I see these things, this is +2, this one's +2, this one's +2. And when they come in here and the 2 electrons, now you end up with CuO. And when you're doing all this oxidation reduction stuff, what's going on? Well, it's 2 electrons are being attached to it. And then you basically have what appears to be deposition occurring. It's really kind of strange. Let's take a look at what's happening on the other end of this thing, so it makes a little more sense. We'll go down. I just want to go down to the cursor. Wow. Okay. The problem with the whatchamacall, honestly, is I love the thing I'm using for Zoom, except my numbers would still be all over this thing and I just can't refer back to it. Look at this guy. So here's my zinc rod. So this is the illustration being made here, and that's kind of the point I'm making with all this stuff. If I find my cursor, where are we? Here we go. Boom, come down a little bit. Okay, so zinc, once again, okay, I'm going to grab a bright color for seeing this thing. These things are all ZNO, right? ZNO, ZNO, ZNO. This is what we start with, right? ZNO. And as these things come off, right, the 2 electrons are going to go off. So I have these 2 electrons are going to go up the rod, 2e, right? That's what's showing here. It's 2e. It's going up. It's going to go across the wire. And that is the form of we call, obviously, electricity. This is how battery works. Electricity goes across the thing, and you guys can see this. You don't have to, I can just illustrate even more, but it goes through here, and then you get basically voltage, right? And I'm not going to get into the Nernst equation and all that. That's for AP Chem, but it comes down, and the concentration, and you think about it, the more concentrated your solutions are, the more voltage you would have. And it has to do with an oxidative reduction numbers that people say, do you have to memorize the numbers? No, not right now. It's not important. We're not going to do that. I'm going to put a break on that, but I'm just trying to show you where this happens. Here's your salt bridge. Now you got to think about this. Eventually, this thing, and that's the weird part of this, it's going to get tons and tons of zinc in here, right? Zinc +2, zinc +2, zinc +2, right? It's eventually going to stop because the charge is so high. So that's why the chlorine comes down here. Chlorine comes down into the solution and it neutralizes the charge. This one too, what happens is if this keeps going this way and getting onto the bar, you know, eventually you'll have a buildup of negative charge in this solution. To prevent that from happening, potassium comes running down, right? So it's going to be 2 of these for every one of those guys that go up the bar. This is the way of preventing it from, I guess, malfunctioning. Does this make a little more sense? I know you guys have been doing this stuff. You're kind of like, well, what good is this? Obviously, this is how batteries are made, okay? Do you know what the first official battery, this will blow your mind a little bit too, right? Everybody know when did they first figure out the first battery was made? You guys would be glad. This is amazing information, right? Never heard this. This is so crazy.
Nikola Tesla.
No.
Nikola Tesla.
Guys, this will blow your mind. This is first discovered, and check this out. I'm gonna change my screen share here. I'm gonna show you something very fascinating. In Baghdad, it's a Baghdad battery. So you got to think of how long ago this was. If you could see this, this is around 250 before Common Era, the 224. So in the excavation of this thing, they found this thing. It's a cylinder. Let's see if we can see if the video plays well. The idea behind it was like this: they had a rod, an iron rod that ran down, and there's two different chemical chambers in here, and they were able to generate electricity. And they can't figure out what they were doing with this. They figured it out, but they don't know really what it was. I mean, it's sort of a weird situation if you think about it. Let me see if I can find a YouTube link, right, for the Baghdad battery. Baghdad battery. It's such a simple but interesting. Let's see how a 2,000-year-old battery could have worked. Wait. Pause. I don't know if I like the way this guy's talking to me. Oh, it's Mr. Engineering Guy. Can you guys hear the volume on this or no?
No.
No.
Okay, I gotta share this with you. Wait, hold on a second. So we can optimize share computer sound. Go back down. And for this, we're going to maybe optimize for full view. And let's do this. All right, here you go. Play.
Prachtige site in which he claimed that 3 artifacts which were found in Iraq used to form a battery, now called the Baghdad battery. Koenig hypothesized that the 2,000-year-old objects, a ceramic pot, a copper cylinder and a rod of iron, were used to create a current. How would that have worked? A battery, like for example the modern alkaline AA battery, has 2 major substances: zinc, the anode, which can release electrons because of oxidation, and manganese dioxide, the cathode, which can use those electrons to start a process called reduction. The 2 displayed half reactions taken together result in an overall so-called redox reaction, which releases 1.43 volts of electricity. The only thing missing is a place for the chemical reaction to happen, which is the function of the electrolyte alkaline, hence the name alkaline battery. That is the basic principle of a battery: an anode, a cathode, and an electrolyte. Now switch the help.
Beg your pardon here. Let me back up for 1 second. Let's let this thing go back 1 second. Can you guys hear me? Can you hear me, right? Okay, so this is all the stuff we've been showing. This is obviously a total chemical reaction like we've been doing, oxidation reduction, but this is in a basic environment. Basic is alkaline. So alkaline is you have earth metals, alkali earth metals. So this would be anything like sodium hydroxide. It's a base that you find centered that's dividing these two different plates. Make sense? So the stuff I'm showing you is kind of interesting in the sense that, you know, you can really focus on this. So the anode, right, is the place of oxidation, okay? So I'm going to actually put this up here. You guys might want to write this down because it makes us feel better as people, right? So how do we memorize that? It's called, ooh, I can't see that. That's weird. Okay, so we're going to put an-ox. So the negative thing is the anode. It's an ox, so it's oxidation, right? The cathode is the positive one, CAT, which is positive. So it's called the cathode, and it's the site of reduction, okay? So some people like to remember it as red cat, right? And this one's known as an ox. That's how people kind of remember what happens at one end. So we know oxidation is giving up the electrons and reduction is receiving it. So we have 2 things occurring. So when you see the negative, of course, that's where the electrons are coming off, and it comes back, and at the reduction end, that's where at the cathode part of this thing. Does that make sense? So I'm going to clear this off so we can see the rest of the video without them bothering us. But I don't know if you guys, let's see if I can just hit play. No, I can't find the play button. Where's the play button? Oh, I have to go back here. Okay. No. It's covered up. I can't see it. Oh, God.
Oh.
How do I get out of this thing? Okay, well, scroll down. All right, good.
An anode, a cathode, and an electrolyte. Now, switch the half reaction of zinc for that of iron, the half reaction of manganese dioxide for the one of copper, and
Oh God. Okay, let's keep going. I don't know why it's giving me such a hard time.
the electrolyte alkaline for a ceramic pot filled with, for example, vinegar or wine, and you've got yourself a working Baghdad battery. But the question is, were those artifacts indeed used for this purpose? Well, probably not. They might have been used for a process called electroplating, or, others claim, the artifacts were used for storing scrolls. Some even claim that the artifacts are not even originating from the Parthian period, but from the Sasanian period, which makes the Baghdad battery about 500 years less old than Koenig predicted. Professor Stone, an expert on Iraqi archaeology, stated that she does not know a single archaeologist who believes that these were indeed working batteries. The first real battery was most likely the one created by Alessandro Volta in the year 1800. But if you would like to know more about that, you can listen to the new podcast I launched today named Age of Technology. Together with my mate Henry, we explore and discuss the history and future of everyday technologies. First,
Well, well, that's a big fine. How do you do, huh? You guys agree with that? So here I am talking about Baghdad battery, and then this guy just basically took a healthy one right on top of it, saying it's probably not what it was. I like that. That makes me feel better about the fact I brought it up. but it's like anytime it's refuting an idea. It's just sort of weird. Why would you have an urn with an iron thing, and then obviously anything you can make a battery out of a pickle if you did it right. You know what I'm saying? You guys have seen that, right? You can take a pickle, you can take anything out of a potato. It's strange. So they might have come up with it, and using it for electroplating, they'd have to run a current through it to make it happen, right? So Baghdad battery. Let's take a look at one from an image point of view, and basically it's just fascinating that these things were created. This is 13 and a half centimeters tall, electrolytic chamber, clay, iron head, asphalt seal. Interesting. Seems pretty elaborate. Internal copper cylinder. So obviously, if we look at cross section of the thing, it almost looks like a AA battery in the sense of how this thing is kind of set up. It's sort of
It's
just
like aliens like brought that to us.
I never know. It's sort of weird. It's just such a weird phenomenon. 2,000 years ago, someone figured this thing out or did something with it, and no one could figure out what it was used for. So, and you never know. Like, they might have figured it out but didn't know what to do with it. They kind of found out, oh, wow, this gives a weird sensation. You put it together, and someone held a wire, and it was a gag gift that you sent people. You sent a gag gift sent to the king. Who knows what the heck? The pharaoh was playing with it. So it's kind of like, I guess, I don't know if anybody's ever tried to make one and see if it functions, but it's strange nonetheless. So going back to our drawing, because that's I put it in paint. This is the only reason why I did it in paint, is then I can view, let's zoom out. Okay. We can actually take a look at some of the stuff we come up with. I got to move my header now back over here for all practical reasons. I think the purpose, I'm trying to show you what's occurring. Obviously, with the Baghdad battery, they had the iron one or the copper one being decided. You couldn't really tell because it's 2,000 years old what happened to what, right? But the idea behind it, once again, is that it's such an interesting phenomenon on how this thing would work. I don't know. I think that one year, I think it was, who did this with me? Ethan Kang and T. We decided to go ahead and we did a voltaic cell. This is AP chemistry at the end. And they wanted to see it. They just wanted to see the metal dissolve. They just wanted to see. And of course, we tried to feel like if there was a current, we put a voltmeter up to it. And it works. It takes a little creativity to make the salt bridge. We did some agarose, and we put a lot of sodium chloride in it, and just kind of hung the thing like a bag. And it's hard to explain. Use dialysis tubing for doing it. It worked pretty nice. Okay. So you can, for all practical reasons, I'm going to draw this picture up right now. We took you guys know what dialysis tubing is? You will know, right? It's a bag, okay, that goes like this. And most of the time, you could turn around and you could tie off the ends. Essentially, is what we did. Okay, and we took three things: agarose, right? We took knuckle, right? Put it both
Knuckle.
knuckle, put it both together and mix it up in here. And of course, you're going to add water, right? And then when it was done, okay, we turned around and we submerged this end into the thing like this. It worked really nice. Go up like this, submerge both ends. You take a pair of scissors, and let's say this is my solution. I'm going to put zinc nitrate here, right? NO3, 2. And on this end, I'm going to pick on this one. I'm going to put copper nitrate, CuNO3, right? 2. And then obviously we put a rod here. Wire goes over here, put a rod over here. And we hook up a voltmeter. Right here is a voltmeter to tell us what the charge would be. And once it's underwater, you take a pair of scissors and you cut it. It's under the solution, cut it too. So now you do have a functional salt bridge. It's kind of a cool invention. And basically you let this thing run and it generates something. We let it go overnight, see how long it would burn. Eventually they peter out because the sheer fact that whatever salt you have is going to run out and you're going to basically deplete. Once the charge is kind of to the point where you have a buildup of, in this case, because this is zinc end, you have a built up a positive charge on one end and a built up of, in this case, negative charge on this end. You basically kill the cell. It won't work anymore. But it's fun, and we can't do it because of coronavirus. But
Wait,
that's,
what about the lab that's still at school?
Oh yeah.
We didn't finish it.
The yellow one?
Yeah.
The lab.
it is what it is. I don't know. All right, guys. So for homework, I'm going to put something up. I want to see your pictures on how you drew this thing. Okay.
Yes.
And that's it. And then you don't have any homework this weekend. Does that sound good?
Yeah.
All right.
Yes.
All right. Bye, Dr. Dick.
You want it in a Google Doc?
Yeah. Take a picture, stick it in a Google Doc. We'll call it a day. Cool.
Okay.
All right. I'll talk to you guys later. Bye.
Bye.
Bye.